So today we are going to demonstrate a program for interfacing to a 4 7-segment displays using shift registers. The programming part is done in Proteus. We begin the program by adding the necessary header files, reg51.h and kjcserial.h, and then we begin by followed by the global declaration of port 2 and port 1. One is for the shift registers, one is for the ST, and another is for CLK. Which is the Clopus. And then we have defined two functions, void byte split and void char split. We will come back to the function later. And then we proceed to the main function. In the main, we have declared two variables, unsigned char data type, H and L. H is for storing the upper byte, and L is for storing the lower byte. And these are the declaration that we had in all our programs. We set P2 equal to 0h00, which is the output configuration mode, and we enter the while always true loop. We are receiving the upper byte from the user and stored it in H using the read byte PCR. We receive the lower byte from the user and store it in N, and then we display both the upper byte and lower byte together as with the message input. And then we call the function char split of h and char split of L followed by char split of h. So that's the main section of the program. Now let's see the functions char split of L and char split of h. So when char split of L is called, the lower byte passed on to L in this session is passed to the function. We have the char split function and we have L passed to it. We have two variables in that, H and L. Here we are dividing the byte we declared into two, upper byte and lower byte. That is, say for example, we have AF as L. We are here to see that H and L, we are A can be taken as H and L can be taken as F. So we have the array over here declared, array A holding 16 values 0 to F. So we have here two set of code. One is for left shift and other is for right shift. After the execution of each, we move to the function byte split. So what does char split do? We left shift the values in this section and we obtain the least bit. Say for example, the value passed is AF. After this set of operations, that is left shifting for 4 times and followed by left shifting for right shifting for 4 times, we obtain the last value, that is F over here. So the AF hexadecimal value can be 10101111. After right shift, after left shift, it becomes 1111. We pops out 1010 again, and the place that is 1111 gets 000 by default. And then again, when we right shift, we get 000 in front and followed by 1111, which is the value of F. This 0000 is added by default. Similarly, on the right shift, we pops out the leftmost element. Say we are popping out F. This can be done just by right shifting 4 times. Say for 10101111, when we right shift, 1010 will takes the place of 1111, and the position of 1010 before the right shift will be taken by 0000. So this value is then taken as the hexadecimal value, which is used to represent the equivalent display in the 7-segment display, and it is passed to void byte split function. So since it's a 7-segment display and has 7 terminals to be activated, we have to take the value. Say for example, what we have here is 0 1 1 1 0 0 1 is the equivalent value for displaying 0f. So when we have to pass this value to the 7-segment display, we have to pass like 0 1 followed by then 1 1 1. So we have to pop one by one values. So for obtaining this value, we are storing t equal to x. T is just a temporary variable, and x is the value that we get from the byte split a of L. So when t is equal to x, say for example, the value we have is 0 1 1 1 0 0 0 1, which is 0 8 7 1, which is 0f. So this is the value of f. For displaying this in hexadecimal, in 7-segment display, we have to pass 0, then 1, then 1, and followed by the other digits. So since we have to display 0 and we have the rest 7 numbers to be popped out, we do a right shift of 7. So after this right shift, we get 0 in the least bit, and which is passed through the SDA to the 7-segment display. After we getting 0 over here, we left shift x equal to x, left shift one time. So the value of x, that is the permanent value we have here, is 0 1 1 1 0 0 1 will get modified into 0 1 1 1 0 0 0 1 0. So the first element which we have passed through the SDA to the 7-segment display is popped out, and we have 8 iterations. We have set the limit to 8 so that we will have 7 iterations. So this is the functioning of the code. This program has been debugged and the hex file has been created. Let's move to the simulation part. So this is the simulation part. We have 8089C51. We have the shift registers connected over here. We use 7HC164. That's the shift registers we have. We have the 4 7-segment display, the virtual terminal connected in serial mode for serial communication. So let's take the simulation of this. Say the upper byte we are giving is 1 2 and lower bit is 2 1. We have the display over here as 1 2 2 1. Execution number 4, check number 2, 1 4 4 1. We have 1 4 4 1. 1 3 2 1. We have 1 3 2 1. 1 5 8 2. So that's all about the program. Thank you.